what kind of alpha? What's the maximum possible value of alpha that makes this sequence less than or equal to e? And what's the minimum possible value of beta that makes this sequence greater than or equal to e? For any value of positive integer of n. Now, the background of this question is, so this is a basic fact from analysis that this sequence is monotonically increasingly approaching e, and that sequence is monotonically decreasingly approaching e as n approaches infinity. So naturally, we're interested in finding out, right, since this sequence is increasingly approaching e, so that means this sequence is less than or equal to e. So naturally, we want to ask, could the sequence, like if we add n plus 0.1, could that new sequence be still less than or equal to e? Right? N plus 0.2, could it still be less than e? Right? Likewise, if we reduce one little bit, n plus 0.9, would that new sequence still be larger than e? Right? That's a natural question to ask. So first of all, let's prove this fact. So 1 plus 1 over n to the power of n is equal to 1 times 1 plus 1 over n times 1 plus 1 over n times 1 plus 1 over n. And many of them. Now, using AM-GM inequality, like geometric mean, after I take the raised to the power of n plus 1 on both sides, it should be less than the arithmetic mean of n plus 1 many elements, and 1 plus 1 over n plus 1 plus 1 over n all the way 1 plus 1 over n. I have exactly n, many of them, right, to the power of n plus 1, right? Because otherwise, if I don't have this power, I would take the n plus 1th square root, right? N plus 1th root here. So that would be equal to n plus 1. That's 1 plus, so n many of them, n times this thing. So n plus 1 to the power of n plus 1. So that would be equal to 1 plus 1 over n plus 1 to the power of n plus 1. Now, so this is really true. So this sequence is an, and that sequence is obviously a plus n. So really the sequence is increasing, right? Increasing. So the next sequence, that sequence. So 1 plus 1 over n to the power of n plus 1. So how do I deal with that? Right, obviously I cannot use the same method, of course, same method, but a little different, because this time I want to change the direction of the inequality. So how do I do that? So that is equal to n plus 1 to the power of n plus 1. That is equal to 1 over n plus 1, n to the power of n plus 1. That is equal to 1 over 1 times n over n plus 1 times n over n plus 1 times n over n plus 1. I have exactly n plus 1, many of them. Likewise, less, so this is, bottom is less than or equal to, so reciprocal is greater than 1 over, still the same method, right? AM-GM inequality. I have n plus 2, many of them, and 1 plus, likewise, this plus this plus this, so n plus 1, many of them. So n over n plus 1 times n plus 1. N plus 1 cancel out. I have n exactly to the power of n plus 2 this time, right? N plus 2 many elements. So that is equal to, take the reciprocal, right? Reciprocal. So n plus 2 n plus 1 to the power of n plus 2. That is equal to partial fraction 1 plus 1 over n plus 1 to the power of n plus 2. What is that? Right, that is, for example, bn, right? So this is obviously bn plus 1. So really, this sequence is really decreasing. Right? The next member is smaller than the previous member. Now, to answer this question, what's the maximum possible value of alpha that makes this inequality true? Right? All I need to do is take logarithm on both sides. So take down the power n plus alpha times log of 1 plus 1 over n. That's less than or equal to log e. That is 1. Right? So, in other words, what kind of alpha satisfies this inequality? Right? So, which means n plus alpha less than or equal to 1 over log 1 plus 1 over n, which means alpha less than or equal to 1 over log of 1 plus 1 over n minus n. Right? So as long as alpha is less than or equal to this expression for all positive integer of n, then I can make sure this inequality is always true. Right? So to find out the maximum possible value of alpha that makes this inequality true. Right? So first of all, I know for a fact that, for example, alpha, for example, take the value of some fixed number less than that one. Take some other fixed number less than that one. Right? So what kind of maximum, so which means all those alphas are lower bounds of this expression. Right? So the maximum lower bounds, right, greatest lower bounds, which means that's the infimum. Definition of infimum is the greatest lower bound. Right? If it has a lower bound. Does it have a lower bound? That's my question, right? So first of all, to find a possible lower bound of this expression, first let me say, is this expression greater than or equal to something? In other words, is the bottom less than or equal to something? Yes, I think so. Because, first of all, log of 1 plus 1 over n, my claim is that it's less than 1 over n. Right? Here's my claim. Because the reason is because I've just shown that this sequence is increasingly approaching e, right? So which means this sequence is less than e. So 1 plus 1 over n to the power of n is less than e, which means logarithm on both sides. N times log of 1 plus 1 over n is less than log of e. That is 1. Which means divide n over, right? Log of this part is really less than 1 over n. So this is really true. Right? My claim is really true. And so since the bottom is less than 1 over e, so the reciprocal is greater than 1 over n, which means greater than n, so greater than 0, right? So the whole thing is greater. So f of n, that's 1 over log of 1 plus 1 over n minus n is bounded below by 0. Right? 0 is a lower bound, but not necessarily the greatest lower bound. The greatest lower bound could be strictly greater than 0. 0.2, 0.3, all possible. Not necessarily 0. But let's find out. So, of course, at the same time, so let me just denote the maximum possible alpha is in fact the greatest lower bound. That's the infimum of, let me denote it as infimum of f of n, right? So n takes any positive integer. So let's find out beta minimum possible value of beta. So in other words, if I take logarithm on right hand side, right? So just change the direction of the inequality. So here I just have to rewrite it into beta is greater than or equal to the same thing, right? The only difference is the direction. So 1 over log 1 plus 1 over n minus 1. So what's the minimum possible beta that makes this inequality true, right? So beta may take many possible values. Each value is a upper bound. Many upper bounds for this guy. So is there a least upper bound, in other words, right? So least upper bound meaning the supremum, right? So in other words, beta minimum is in fact the supremum of f of n, and takes all possible positive integers. Find out its supremum. So the question is that, does it even have a upper bound? Is it bounded above, right? If it's bounded above, fine, it has a least upper bound, right? I say yes, it's really bounded above. So in other words, I just have to, so here's my other claim. 1 plus, so log of 1 plus 1 over n is really greater than or equal to 1 over n plus 1. Here's my claim. The reason is because I've just shown that this sequence is decreasingly approaching e, which means the sequence is greater than e, right, that sequence. So which means because 1 plus 1 over n to the power of n plus 1 is greater than e. In other words, log, right, so take down the power. Log of 1 plus 1 over n is greater than log of e, that is 1. So divide by n plus 1 over. So that gives me this inequality, right? So this is really true. So really this guy is bounded below. So the reciprocal is bounded above by n plus 1. So n plus 1 minus n is n, bounded above by 1, right? So not only greater than 0, but less than 1. So let's write it here, less than 1, all right? So this is cool. So yes, really, so bounded above, that's why it must have a least upper bound, supremum. So now let me have a look at the function. Look at the function. I say function of f of x, that is 1 over log of 1 plus 1 over x. Just replace n with x minus x, where x, of course, is between 0 and positive infinity, excluding 0. Now my job is to look at its derivative, right? Since we're talking about maximum minimum, so find its derivative. First of all, negative 1 over log of 1 plus 1 over x. Altogether, quantity to the power of 2. Right. Chain rule. Chain rule tells us to differentiate the since I treat log as a whole entity, right? Then composed with that. So differentiate log. Right? So take the reciprocal of 1 plus 1 over x. That's x over x plus 1. Also differentiate the inside function. That is 1 plus 1 over x, right? 1 will be gone, and so 1 over x becomes negative of 1 over x squared. But negative cancel out, right? And x squared and this x gone. So again, minus becomes minus 1. So derivative becomes, let me just write it neatly, x times x plus 1 times log of 1 plus 1 over x quantity to the power of 2 minus 1. So now we found the derivative of this function. So of course it's a complicated one. So next I want to make some substitution. Let's say I want to let 1 plus 1 over x equal to e to the 2 times u, where since x is greater than 0, so 1 plus 1 over x is greater than 1, so which means u is greater than 0, right? U is greater than 0. So why don't I use substitution e to the u straight away? So the reason is because I tried, but it didn't work out. So turns out e to the 2u is the more suitable one, because it will give us something that's nice. So now I can easily work out x, right? So minus 1 on both sides, take a reciprocal. 1 over e to the 2u minus 1, right? So in that case, my x plus 1 would be equal to e to the 2u minus 1. Top I have e to the 2u. Okay? So x times x plus 1 gives me e to the 2u minus 1 quantity squared. And of course, log of 1 plus 1 over x will give me log of e to the 2u, that is just straight away 2u. So let me work out the, so this part, x time. So that is equal to 1 over x times x plus 1. That is equal to e to the 2u over e to the 2u minus 1 squared. And times this part squared. So this part squared, 4u squared. Right, 4u squared. Then minus 1. Of course, take its reciprocal. That's flip this upside down. So flip e to the 2u minus 1 square. Right, so there's no more. And just rewrite it into, so expand everything. Expand bracket, right? Expand bracket. I have perfect square e to the 4u minus twice of e to the 2u plus 1, I believe. Then divide e to the 2u up, right? Simplify that. So e to the 2u, this becomes e to the 2u, and this becomes minus 2. This becomes e to the negative 2u, all right? So this is good. This is good, and this is also a perfect square, right? E to the u minus e to the negative u square. Right, minus e to the negative u square. Right, this is perfect square, top. 4u square minus 1. Right, so that is just, so the derivative, just rewrite the perfect square, combine the perfect square. Right, just half u squared. 2u e to the u minus e to the negative u and quantity squared, the minus 1. Right? Right, so just without the u, inside half of this thing, I just have this sinh, right? Sine, hyperbolic sine. Now I want to have a look at inside the square, except the u. I want to have a look at half of e to the u minus e to the negative u, right? That's the hyperbolic sine. My claim is that this thing is greater than u when u is greater than 0. Here's my claim. The reason is because if we just take the so greater than u, right? Here's my claim. So all I have to do is to look at the this function in u, function of u, half of e to the u minus e to the negative u minus u, is it greater than 0 when u is greater than 0. So all I have to look at is its g of u, right? So g prime of u, what's its derivative? So half of e to the u minus plus e to the negative u minus 1, right? When things, so this I use the AM-GM inequality, right? Here's the arithmetic mean. So greater than or equal to its geometric mean. So this e to the u times e to the negative u minus 1. So that is equal to 0. Right? Derivative is non-negative, which means the function g is increasing. Right? What's g of 0? G of 0. E to the 0 minus e to the 0. 1 minus 1, 0, 0 minus 0, 0. Right? So which means g of u is greater than g of 0. Right? Increasing function when u is greater than 0. Right? So which means this is really true, right? Really true. So that is really true. So like I said, half of e to the u minus e to the negative u is already greater than u. When you divide it by u, it's greater than 1. Right? 1 to the power of 1. So greater than 0 when u is greater than 0. Right? So which means the function derivative of f is greater than 0, which means the function of f is also increasing, right? When x is in this region, right? Also increasing function. So now I can successfully answer the question, what's the maximum possible alpha? That's the infimum of f of n when n takes all possible positive integers. Right, so out of all the positive, f takes all the possible positive integers, what's its infimum, right? So imagine you have a, look, I've just shown f is increasing, right? X is greater than 0. So since x this time takes positive integer, so f of n will be greater than or equal to f of 1, right? Discrete version, right? Increasing f of 1 will be the smallest when x takes positive integers, right? So the infimum out of all these possible values, what's its least greatest lower bound, right? Lower bound. F1 is down here, F2 is up here, F3 is up here. Well, what's the greatest lower bound? Right? This is lower bound, this is lower bound. What's its greatest lower bound? F of 1, right? So alpha of maximum is infimum, that's f of 1, right? That's log 1 over log of 2 minus 1, right? So that's approximately some 0 point, don't remember, something, 0.44 something. So which means if you take any alpha value that's even the slightly bigger than this number, you will end up in a situation where there is some n which makes the left-hand side bigger than e, right? So that's the maximum possible value alpha can reach that makes the left-hand side inequality still hold, right? So what's beta minimum? The smallest possible beta, right? So in other words, f of n is supremum, right? I've just shown f of n is not only bounded below but also bounded above, right? So the function will look like something like this, f of 1. F of 1 is somewhere here, right? Somewhere here. Increasing function, but bounded above 1. Perhaps here's 1. There's also 1. F of 1 is here. Increasing, bounded above by 1. Bounded below by 0. Right? Perhaps it's something look like this. I don't know. Maybe look like this, right? So here, bounded below, increasing, like this. So, what's its supremum? Right? Supremum. Obviously, the supremum of all the function f of n is just not necessarily 1. Not necessarily 1. 1 is an upper bound. Least upper bound may not be 1. Least upper bound is the limit as x approach positive infinity, right? Intuitively, it makes perfect sense. F of positive infinity. So in other words, we want to calculate the limit n approaches infinity of f of n. That would be the smallest possible beta. Now to calculate the limit of f of n, I say, right, n approaches infinity, so 1 plus x, Maclaurin expansion nearby 0, log of 1 plus x, when nearby x equal to 0, right? So all we have to do is to, first of all, log of, so f of n, I rewrite this, 1 over log of 1 plus 1 over n, Maclaurin expansion, first term, 1 over n, second term, minus 1 over half n squared, and plus 1/3 of 1 over n cubed, but we don't need that. All we need is a little o of 1 over n squared. That's what we need. So again, so what does little o mean? Little o just, you can just treat little o as a sequence that's approaching 0 as n approaches infinity. Right? A sequence that's approaching 0 multiplied by 1 over n squared. So the whole term is approaching 0 faster than 1 over n squared, right, intuitively. And minus n. Now, okay, so this obviously undetermined, right? Undetermined because the approaching zero, 1 over 0, approaching positive infinity minus positive infinity, undetermined. So the correct way, so one of the correct way to deal with that is equal to the 1 over common denominator. Let's use twice of n squared, and I have twice of n minus 1 plus. So after I factor out 1 over twice of n squared, I have little o of 1. Little o of 1. Like I said, the reason is because little o can be viewed as a sequence that's approaching 0. Right, just separate them out. Right, you just factor out 1 over 2n squared, right? And but little o of 2, but it's the same as little o of 1. Right, that's the same. So minus n. And of course, we're going to flip it upside down twice of n squared, right? And to work out this, of course, we're going to 2n minus 1 plus little o of 1, and 2n squared minus n, common denominator is this, minus 2n squared minus 1 minus n plus n, and little o of 1 times negative n is negative little o, but it's the same as positive little o of n, right? Little o of 1 times negative n, right? This becomes plus. It's the same thing. Right? That's easily verifiable. Right. The reason is because little o is a sequence that's approaching 0. But that sequence is not unique. Just imagine it's some sequence approaching 0, not unique. So divide everything by n. Right, divide everything by n. We have divide everything by n squared. No, divide everything by n because 2n squared and negative 2n squared gone. So divide everything by n. I have 1 plus little o of 1, right? Because n divided by n is 1, little o of 1. And 2 plus minus 1 over n plus little o of 1 over n, right? And as n approaches infinity, little o of 1 approaches 0, right? 1 over n gone, right? Disappear. Little o of 1 over n, right? Of course, disappears even faster. So I say approaching half as n approaches infinity, right? So limit of f of n is really half. That's the smallest possible of beta can take, right? Not smaller than that. If beta were a little bit smaller than half, 0.4999999 something, then all of a sudden this sequence will be not necessarily greater than e. There there will exist some n which makes this sequence less than e.